Welcome to my talk. Today we'll talk about the reduction from the path traveling salesman problem to the traveling salesman problem. This is joint work with Vera Traub and Jens Fie. So we briefly introduce those classic problems. So given it's an undirected graph and non-negative with non-negative edge length. In TSP, the goal is to find a way to traverse the edges such that every vertex gets visited at least once and we come back to the vertex where we start. And the goal is to do so using the shortest total distance that's being traversed. That's equivalent to finding a shortest Eulerian subgraph. So there's a subgraph. So when I talk about subgraphs, I always allow for taking edges multiple times. It's actually about these sub-multigraphs. The same when I talk about subsets of edges. So we want to find a connected subgraph with even degree everywhere. In path TSP, the task is to find a way to go from S to T. Start and endpoints are different here, but again, you want to visit every vertex at least once. So this corresponds to finding a subgraph that has even degree everywhere except for S and T, where degree is odd. So here are potential solutions for TSP and path TSP. And of course, those graphs are precisely the ones with the property that you can then find such a traversal going over each edge precisely once. There's an important special case known as the graph version of these problems. And so it's the case where all the edge lengths are equal to 1. So we're interested in approximation factors, approximation algorithms. There's been a lot of activity recently. And so we just introduced two versions, the traveling salesman problem and the path version thereof. And then for both of them, we have the graph versions where the edge lengths are 1. This leads to 4 versions, here represented by each by one color. Maybe let's start with the classical TSP problem. So it's the blue line. So here we have an old algorithm from the 70s by Christofides and also from Serdyukov. There's a 1-to-5 approximation. So this one has only been improved for the special case of graph TSP, just the green line we see here. And so this is started with a slight improvement by Ovis Gara and Saberi and Singh, and now we have a 1-to-4 approximation by Sheba and Fegan, which is currently the state of the art. For the path version, there's typically be quite a gap to the path version. For example, for path TSP, so the red line, Hogeven observed that Christofides-Serdyukov's algorithm, and just adapted naturally to the path version, is only a 5/3 approximation, but not a 1-to-5 approximation. And this has been improved by Ann Kleinberger and Schmois in 2012, and then has been successively improved, and only very recently, we've been able to match the 1-to-5 approximation factor of Christofides and Serdyukov. So here, this gap between path TSP and TSP got finally closed after quite some time. However, for the graph version, that's not the case. So for the graph version of path TSP, the orange line, you see that only very recently we have a factor that's actually slightly below 1-to-5. And there's still a significant gap between TSP and its graph version. That would be the orange and the green and the orange line. Of course, this raises a general question. It's clear that the path TSP problem is more general than TSP, so it's normal that the approximation factors are worse, but it raises the question whether this problem is indeed strictly more difficult to approximate than the traveling salesman problem. And the main result of this paper is that to answer this question by showing that that's not the case. So it turns out whenever you have an alpha approximation for TSP, you can transform it into an alpha plus epsilon approximation for path TSP. And actually, this transformed algorithm will make a strongly polynomial many elementary operations and oracle calls to the original TSP algorithm. Moreover, one important property of the reduction is that the algorithm that is obtained through this black box reduction, the A bar here, they'll call the TSP algorithm only on instances that are subgraphs of the original instance. So here, for example, let's look on the left-hand side, you have a path TSP problem. And on the right-hand side, so a potential call could be as shown here to where we call the TSP algorithm on this subgraph. So this is important because this implies that if you start with a graph instance, then also the calls to the algorithm A are calls on the graph TSP instance. Therefore, approximation algorithms for graph TSP will also carry over to the path version of graph TSP. So this immediately implies that that gap I highlighted before can now essentially gets closed. So with resolve VM behalf, you can now get a 1.4 plus epsilon approximation for the graph version of TSP. But I think what is more important is that from now on, this discrepancy between approximation results of TSP and path TSP is gone up to a small, an arbitrarily small error, even if further improvements will be found soon. So let me say a few words about the reduction. So let's go first for a very canonical reduction idea, a canonical way to reduce a path TSP to TSP. So what one could do is one could simply, instead of given a path TSP instance, one could simply solve first a TSP version, solve TSP on the same instance. This could lead to a solution as shown here in orange on the left-hand side. And then, of course, that solution is not a path TSP solution because the degrees of S and T are even, but should be odd. So this can be fixed by adding a shortest SD path. So let's just try, this is going to be a very canonical idea. Let's just try to briefly think about how much, what kind of approximation guarantee we get through that very naive reduction. So everything here is based on the simple observation that the optimal solutions for TSP, the length of the optimal solution for TSP, and in some years for path TSP, that they differ by no more than the distance between S and T, because one can always add such an SD path. And so it turns out that, therefore, we can get a 1 plus epsilon times alpha approximation for path TSP if the distance is small enough, the SD distance, and small enough would mean in the order of epsilon over 2 times the length of opt. That's, of course, very small, and the main question is, what should we do, or what can we do if the distance is large? So we build up on a technique that was originally introduced by Bloom, Chowlock, Carter, Lane, Meyerson, and Minkoff, and later extended by Traub and Fegan. And this technique, was in both of those papers, is used to reduce instances where the SD distance is larger than a third of opt, of the length of opt, to instances where it's about a third, so a third plus a small, and delta times the length of opt. So it's a warm up because we only get to a third of opt. We need to have much less, as we saw before. We need to have in the order of epsilon times opt. But it shows many of the ideas we want to use later on. So let's look here maybe just at the or maybe first to simplify things. Let's just assume we're in a graphic case, so all the lengths are equal to 1. So here's here in the box a potential optimal solution to a graph TSP problem. And so what we do is we first define a chain of SD cuts, so 0 to L8 in the example, where Li are simply all the vertices whose distance from S is no more than I. So the idea is that we will try to guess in those, we look at those cuts and try to guess which one of those only have a single edge of opt. So this will be those with the blue ones here. And we also want to guess the edge of opt in this case. So for this, let's first, let me first just highlight that it turns out there will be many such cuts if the distance from S to T is very large. Let's just do maybe a little thought experiment. So assume that the distance from S to T is actually even at least a half of the length of opt. So in a graph case, the length of opt is simply all the edges and opt. But in that case, so what's important to observe is that for any SD cut, a path TSP solution has always an odd number of edges in an SD cut. Therefore, it's either 1 edge or at least 3. So, I mean, you immediately see it's impossible to have no 1 edge, for example, in those cuts from L0 to L8. So the number of SD cuts we have is equal to the, corresponds to the distance, right? So it's impossible because in that case, we would have half opt many cuts, each having 3 edges. This would lead to 3 half opt many opt edges, which of course is a contradiction. So, and one can now just do the math to check that the total number of edges of, the total number of small cuts with a single opt edge that we have would actually be, if the original distance is a third plus delta times length of opt, then you will have at least that many cuts that are small. So the trick is then that we use dynamic programming. We can use dynamic programming starting to guess those small cuts from left to right, starting from L0 going to L2 and so on. What is a key property here in that procedure is that, so if you guess, for example, the cuts L2 and L5, then you still have to solve the sub-instance in between, this instance here. So U and V are the two vertices that have been connected to the outside, but that sub-instance is again a path TSP instance. So, so what one can do is one can actually just recurse on that sub-instance. Another observation that's important is, as I mentioned before, if you guess once opt edges and small cuts, then we actually even guess a constant fraction of opt. And so therefore, if we recurse, if this happens more often, we need to start guessing a significant fraction of opt. Therefore, at some point, we will end up with sub-instances that, I mean, either we will almost have guessed all of opt, or we'll end up with sub-instances where the distance from S to T, or in this case from U to V, the distance between 2 points in a sub-instance is not much larger than a third of the optimal solution of the sub-instance. This can be extended to the weighted case, the case where the general length case. What one can do here is simply look at an optimal dual solution to the shortest SD path problem. This will be again a chain of SD cuts together with non-negative values on those SD cuts that fulfill certain conditions. I listed here on the right hand side. Maybe we don't need to go into those specific details. But it turns out one can again prove that even in that setting, the light cuts, the cuts with a single opt edge, they will actually, those opt edges that are crossing there, they will also have a total length of at least 3/2 times delta times length of opt. So even here, you may not have many of those cuts, but you're sure to have a significant fraction of opt length in those cuts, with significant meaning a constant fraction. And again, one can do a dynamic programming approach to guess those cuts and recurse in the subproblems. So what we do is actually, on a high level, we do kind of a naive extension. We just try to guess cuts with up to constantly many edges. But the challenge is here lies in, there will be a couple of technical challenges we have to overcome that didn't appear in this previous case. So one advantage is, let's assume you just guess any cut with at most 4/epsilon many opt edges. This implies that if the distance is larger than epsilon half times the length of opt, then actually we will guess a constant fraction of opt named in epsilon 4 fraction of the length of opt. So that's good. So because either distance is smaller or equal to epsilon half times L opt, and in that case, the path TSP and TSP problems are almost the same with this canonical reductions at the beginning, or we will guess a constant fraction of opt. The key issue is that the subproblems are not path TSP problems anymore. And this is what we have to address. For this, we introduced the notion of phytors, which is one way to capture those subproblems. But let's just start on the example first, here on the example on the left-hand side. So you see again the same instance we had beforehand, where we get some opt edges shown as thick blue edges here. And so what we do is, let's just look at the subproblem between L1 and L3. So the red vertices you see here are the vertices incident to one of the opt edges we guessed. There are two types of those, squares and circles. So squares are those that have been touched by an odd number of blue edges, and therefore they need an odd degree in the subproblem to have even degree overall. And the circles are those that have been touched by an even number of opt edges. So we call this the interface, those red vertices, and the squares are the T vertices. Moreover, we actually also guess the how the different interface vertices have to be connected to each other. So again, if you see on the left the opt solution, there, so in green you see what I like to call a cluster. So you can look at this cluster here, right? So this just means that those three interface vertices will be connected to each other by the solution, or have to be connected to each other by the solution when I find it. So let me just recast things in a more abstract way. So what I just did is I defined what I'd like to call an interface. So an interface consists of so-called interface vertices. The vertices I, the red ones. A subset of those is in T, and we have a partition on the interface. And what's the task? The task is to find what I like to call a phi tour. You can see this here on the right-hand side now. So phi tour is a subset of edges in that subproblem such that every vertex that is not on an interface vertex has to be connected to an interface vertex. The degrees of all vertices is even, except for the T vertices where the degree has to be odd. And the interface vertices in the same cluster must be connected to each other. Maybe one thing I want to highlight here is it is legal to actually connect two different clusters. So we allow for that, even though the guessing told us that they can be separate. So this will be called a phi tour. So let's start with a special case of phi tours, namely if the set T is empty. So here actually, so this is kind of closer to a TSP problem because all the vertices need to have even degree. It's not quite a TSP problem because we don't need to connect all the vertices to each other, but we can have connected components corresponding to the clusters. However, we can show that one can reduce that to a regular TSP problem simply by actually guessing a subset of the edges used, of expensive edges used. And this can be done in a running time. It's exponential in the interface size. But we will only deal with constant interfaces. Therefore, there will be a polynomial procedure. So the T equals empty set case is very close to TSP. And this again leads to a similar, to an approach of a similar flavor as what we discussed for path TSP. So one that we can do for a general phi tour problem is you can simply first solve a related problem, the phi bar tour problem, where we simply replace T by the empty set. We can do that by using the above algorithm, the algorithm guaranteed by that theorem. And then we can compute. So this leads to a solution with the only reason why it's not a phi tour is that the vertices of T have even degree instead of odd degree. And this we can fix by adding a so-called T-join. T-join is precisely a subset of edges that corrects those parities at T. It's a subset of edges with odd degree at T and even degree at all the other vertices. And we return the union. One can again check how what kind of approximation factor we obtain that way. And so not surprisingly, this extends the path, the simple example I showed at the beginning for path TSP. So it turns out if the length of such a shortest T-join is small, most in an epsilon fraction of opt, then we actually get a 1 plus epsilon approximation with that reduction. But of course, this could be this doesn't need to be the case. We could have could be the shortest T-join is actually very long. So therefore, what we're doing is the following. I can mostly explain on the picture. So here's a phi TSP problem. We first compute an optimal dual solution to the minimum T-join problem. So it turns out that using techniques, combinatorial uncrossing techniques, this dual solution can be described as follows. It's a laminar family of sets, of vertex sets, so cuts. And those cuts are actually T-cuts. So T-cuts means that each one of them contains an odd number of vertices in T, so an odd number of squares here. And together with that laminar family of T-cuts, we have a non-negative value for each one of those. They fulfill certain properties due to strong duality. But so what we're doing here then is we're actually guessing for each one of those T-cuts. So we guess whether it's a small one that contains only a small number, a constant number of opt edges, let's say 8 over epsilon, and we also guess the opt edges that cross the cut. Now this will break the instance into a couple of independent independent phi tour problems. Let's have a look at the white one, the one in the center. So here, a phi tour problem where the interface vertices are this one here and this one here. another one. So again, I use squares to indicate that those are the ones in T, so they need to have odd degree inside. This one here needs even degree inside because this touched an even number of blue edges. Again, 2 with odd here, 1 with even here. Yeah, so I can make it clear. Good. So I want again to guess the clusters, so how those interface vertices will be or must be connected inside. What's important though is that the number of the interface, actually the size of the interface increased. So as you see here, actually a couple of cuts is 1, 2, 3, 4, 5, 6 cuts actually. That where we guessed opt edges and whose edges can contribute now to the white subproblem. So the total number of such cuts that can contribute can't be larger than the original interface, or even be more precise than the original number of T vertices in the outer interface that we have. But still, the interface size does increase, and so actually increases by a factor of about 1 over epsilon. So we have to watch out that we don't do this too often. But again, the main idea will be we only do this for a constant recursion depth, and therefore things will be fine. So we guess those opt edges, solve the subproblems, and put things together. So in short, whenever we have a 5-tour instance, we first compute the shortest T-join. If the one is very short, then we can solve immediately the problem by reduction to TSP, and by direct reduction to TSP without any recursive calls. If not, then we construct this laminar family, guess opt edges, and then solve them and guess the interfaces and recurse on subproblems. Quick explanation why this makes sense. So the main idea is the following. So maybe I'll just give a quick talk briefly about the example here. So let's start with some path TSP problem. Let's say in the first guessing step we obtain 5 subproblems, 5 TSP subproblems. So there are 2 types of subproblems: those with a very short minimum T-join and those with a long one. So the green ones are the short ones, and I drew in red the ones that are long. So the green ones can be solved immediately. But for the red ones, I have to recurse. And again, I have to guess more edges, I get new subproblems, and I keep going. So in the right half of the slide, I highlight how the different quantities develop. But maybe the most important one is the last column here, which indicates what is the total length of edges we didn't guess so far, total length of opt edges not guessed so far. So after a first step, we guessed an epsilon 8 fraction of the opt edges. So only that many the opt edges that we didn't guess so far have length no longer than that. And in the next iteration, the next recursion, we this 1 minus epsilon 8 will square, and so on. So you see that think of those as what we still have to as opt edges, we still have to guess or approximate in the subproblems that we have to solve at the corresponding recursion level. But this implies that after a recursion depth of about 1 over epsilon, log 1 over epsilon, the impact of the remaining open problems will be essentially negligible compared to opt, and we can actually use for those even a weaker approximation, more precisely use a 4 approximation based on Jane's iterative rounding procedure. And putting all that together leads to the final result. Then briefly conclude. So again, any alpha approximation for TSP implies alpha plus epsilon approximation. For path TSP actually showed something a bit stronger. That's even true. It implies an alpha plus epsilon approximation for phi TSP as long as the interface size is constant. And the immediate implication is for graph path TSP, we get the factor down from almost 1.5 down to 1.4 plus epsilon. But I think more important is that there's a discrepancy between path TSP and regular TSP is now gone also for future, also regarding future developments in the field. So many open questions, like we could try to extend such results to the asymmetric version of path TSP. There's already a reduction known, but then one loses a factor of 2. And another extension would be to try to extend those results to so-called T-tours. Okay, thank you very much for listening.